All right, so I hope all of you had a nice Thanksgiving. And so let me tell you a little bit about the schedule. We don't have too many more days left. So today I'm going to do a short, not short, but a review of what was covered in that video that I pre-recorded video that I did last Wednesday. Just do a quick review of that. And also, I will show you an additional video from the StatKey website on randomization tests. So that'll be pretty much what we'll cover today. And then on Wednesday, I will be going over all the different types of randomization tests that we could possibly have. I'll have several examples for you. Just give you complete step-by-step guidelines on how to do these. And so that'll be Wednesday. And then next Monday will be quiz 9, which was everything we covered this week, and including the video from last Wednesday. And what else? And possibly the end part of confidence intervals that we did not cover in the last quiz. That is the difference in the confidence intervals for difference in means and difference in proportions. I see somebody mentioning no quiz. Yes, no quiz today. All right, no quiz. So if there's any questions about quizzes, it's in the schedule of the quizzes next Monday. All right, so next Monday is our quiz, last quiz, and then a review for test number 3. And test number 3 will be next, a week from Wednesday. That's when test 3 is. All right. Then we'll cover everything since chapter 14. So probability and all the chapters on probability, and then confidence intervals, hypothesis tests, basically. Then, so that'll be a week from Wednesday, and then the Wednesday after that, which I believe is the 16th, if I'm not mistaken, is your final exam, which will be from 2:45 to 4:45. I'll have to double check. I'll let you know for sure, but I believe that's what it is. And that will cover the whole semester. And there's 2 parts to it. There's an hour for the core final, which will not be the typical final exam where we will be doing no multiple choice or anything like that. It's basically you'll be printing out something and filling it out. I will have to figure out, I'll have to ask the department exactly how you should be submitting that to me. Now, some of you may not have the ability to scan that part of the exam to me, so I'll have to figure out exactly how we'll do it. And then the second part of the exam is going to be the multiple choice part, like the other 3 tests. So that will be easily done in Canvas. Okay, so I'll contact the math department.
Professor, I have a question.
Yes. Mm-hmm.
So you said the first part of the final test. What is that going to be? You say something about scanning in,
Well, I'm not sure. Yeah, I'm not sure if all of you have the ability to scan and email me the first part of the test, which is basically you'll print it out. You know, I can send you what it is. You'll print it out and fill it in yourself during the test period, but it's not going to be multiple choice or fill in the blank or anything like that. It has to be, I think, on paper. So I have to figure out a way for you to get that to me. All right. So don't worry about it. I'll call the math department and I'll come up with some idea of how to do that. You may have to drop it off at the math department. I'm not sure.
Can't we just take a picture?
Well, some people,
and then send it to
I know. Yeah, I'm getting echoes there. Yeah, obviously, if all of you can do something like that, it's just the clarity of it has to be really clear. All right, it can't be fuzzy. It can't be where some of it I see and some of it I don't see. It has to be crystal clear. Otherwise, you're not going to get credit for the stuff that's not clear. So let me talk to them to see what they suggest for that. All right. As opposed to, taking a picture. But I'll get back to you on that. The other thing also, last time with the last quiz, there were some of you who had issues with loading the StatKey pictures. And they're basically, I believe they were saved as PNG files, but they're picture files. And some of you are having trouble loading them. Some issues with maybe pop-ups. I'm not sure what the issue was, but what I'm going to do for you guys is sometime by Monday of next week, I will have like a test quiz file or something you can go into and I'll put one of those in there and you test to see if you're able to pull it up. All right. In a real Canvas type situation. So it'll be a test for you to see if it's working. And if it's not, then you have to make sure that you're on a computer that does have that ability, or you have to reboot your computer, whatever it might be. But I think that's one way of getting around that, is that you should do a little test. That's going to be important also for the final exam. You don't want technical issues, that sort of technical issues in the middle of your final exam. That would be really bad. So just make sure your computer's up and running. You have no technical issues, and get to a computer that you can count on when you're taking your final. Okay, but I'll put that test thing out, like Sunday night or something, and that way you can test your computer before you take your quiz. All right, does that sort of make sense? All right, so anyway, let me review. What I'm going to do first is I'm going to review what was covered in that video, just to go over it again. And then we'll listen to a video, which is from the StatKey website, about how to do hypothesis tests in StatKey. They're called randomization hypothesis tests. It'll give you an introduction to it. And then on Wednesday, we'll actually do real examples of that. All right. So let's get to, I'm going to get to the textbook first. Let's see, here you go. All right, just to go over a couple things in the text. Now, the textbook, that if you go in the syllabus, there's some material from chapter 13 about hypothesis tests. And actually, let me take a quick look at chapter 13. See what's there. So 13.1 and 13.2, maybe, I think is what you need to look at. But there's also some things in there that are not going to be covered, such as the statistical tests for contingency tables, the type of tables we dealt with before. That's typically not something that's covered in a first-year statistics course. So we're not going to be covering that. But you can look through it anyway. It's part of the syllabus. I don't know why they put it in there if it's not really going to be applied. Chapter 15 is a little bit about using simulation. 15.1 and 15.2, which you can read through. It just gives you an idea of how simulation works. And then chapters 22 and 23 are just a couple different sections in there about hypothesis tests, but I'll go through that now with you. Chapter 22 just gives you the introduction of what a hypothesis test is, and then gives you some basic steps of how to do it. Now I will go over in the handout the idea of hypotheses, that there's a null hypothesis and an alternative hypothesis that has to be stated. It has to be stated symbolically on your final exam. So as opposed to the book here where they just write things out in English, that's not going to be acceptable in the final. You have to actually use symbols. So I'll show you how to do that. Step number 2, they talk about a test statistic. That's geared towards using formulas, which we're not going to use. So that's a formula-based step. stat key is what we're going to use instead of that. We're going to be basically doing step 3. Instead of using the test statistic, we'll use stat key to determine if the null hypothesis is whether we reject it or not. And then we're going to make a decision. The decision step also I will be going over on Wednesday. All right. So again, they talk about the 2 hypotheses here, the null hypothesis and the alternative hypotheses. We give the example of the jury trial, which is what I went through on the video, last Wednesday's video. And if you listen to the whole thing, you know there was a video within the video with Dr. Williams, and she went over this also. So hopefully that was clear as an analogy to what a hypothesis test is. It's basically a criminal trial. And then they give, in the book here, they give some examples with proportions, but these examples do have formulas in them, so we don't want to go over that too much detail, but they do talk about the 3 types of tests that I mentioned in the video on Wednesday, the 2-tail test, and then a left tail or lower tail test, and an upper tail or right tail test. And I'll go over those again in a few minutes. They do mention it in the text here. Most of this is not, this part here, definitely don't pay attention to it. Test statistics, not really use it. 22.4, it is covered in the syllabus, and they talk about the 2 types of errors that we can have in hypothesis tests, the type 1 and type 2 errors. Again, they use the example of a criminal trial to understand what a type 1 and type 2 error is, and I'll go over that again in a couple of minutes. They also mention you are responsible for these definitions here for false positive or false negative. Let me just give you an example of false positives and false negatives. For example, if you got a COVID test, and maybe many of you think that COVID tests are 100% foolproof. They're not. So if you get a positive COVID test, it doesn't mean that you have COVID. And if you get a negative COVID test, it doesn't mean that you don't have COVID. You could have COVID. So there are mistakes that are made in these tests. A false positive would be a case where your test shows you have COVID, but you really don't. And a false negative would be showing that you don't have COVID when you really do. So I'm gonna compare this to the types of errors, the type 1 and type 2 errors that I mentioned in the video on Wednesday, and talk about that in a couple of minutes. Right? They're mentioned here also with reference to the courtroom trial analogy. All right. Probabilities associated with these types of errors. There's the type 1 error, which again I'll explain. The probability of that is called alpha. It's the Greek letter alpha, and it's also called the level of significance. The type 2 error, which I'll talk about, is called beta. We're not going to spend a whole lot of time in beta. The only thing you need to know about beta is what it is, the definition of it. But we're not going to be using it very much. And then it also mentions the power of the test, which I also will mention to you in a couple of minutes. But so you're actually responsible for the definition only. This is a more advanced topic that you would take in an intermediate statistics course, but not in an introductory course. But the definition of it, you should know what it means. So I'll explain that in a minute. All right, and then it explains when to reject the null hypothesis using, now in the book, we talk about this concept called a p-value, which I will explain to you in more detail on Wednesday. The video I will show you today does talk about the p-value, but it may not make much sense to you until I show you examples. The best way to learn p-values is to do examples with stat key. We're going to use stat key as an example of it, but the formulas that you see here, standardized errors, standardized scores, don't worry about those. We're not using any of those for the hypothesis test that we'll be doing. That's chapter 22, and then chapter 23 is just a continuation of hypothesis testing. And in this chapter, I believe it's just the first 2 or 3 sections that you need to look at. Reading through it, there's no harm in looking at it. I don't know if it's going to be very helpful to you in doing the test. I think the best thing, like I said, is to just do examples. Actually, I think I might be into this chapter, so let me get back to the beginning of it. This chapter, there's a whole bunch of things that are way too advanced for this course. So just pay attention to the very first section, for sure, where it talks about the steps of hypothesis tests. Again, we'll be doing step 1. We'll be doing something similar to step 2, except without formulas. Step 3, I'll show you how to determine a p-value. Again, it's easy using StatKey. And then 4, the decision step is something we will learn how to do also on Wednesday. All right. Well, we will be doing exactly what they say here, but it'll make more sense to you on Wednesday. All right. And then on Wednesday, we will be testing hypotheses about both proportions and means, single populations, and also for 2 populations where we will be testing hypotheses about the difference in proportions and difference in means. So there'll be 4 different types of hypotheses that we'll be looking at in StatKey. This section here, when it talks about standardized scores and t-tests, and don't pay attention to any of this. None of this will be used in the way we're going to be doing it. All right, so the first section in chapter 22, certainly for sure. And if you want to read through the next couple sections, you can, but for some reason, I don't know why they picked sections in here where formulas are used as part of the syllabus, and we're told specifically that you're not going to be using formulas for this. So I'm not sure why. Maybe they are using an older edition of the textbook. But don't worry about it. I will have you trained properly in all of this. Now let's go through the handout that I posted along with the video on Wednesday. Let's get to the beginning of this handout. So a hypothesis test. Now, if you remember a confidence interval, let's talk about confidence intervals for a minute. Purpose of a confidence interval is to estimate an unknown population parameter, such as a population mean or population proportion. And the only thing that we get from a sample, if we have a mean, is our sample mean. So what do we do with sample mean? We add and subtract the margin of error if we were going to use formulas, and we come up with an interval called the confidence interval. If we're using StatKey, we would use Bootstrap confidence intervals using the technology that they have. But the whole idea is to estimate an unknown population parameter, such as a mean or proportion. Now, hypothesis tests really goes the other way around. Somebody has proposed sometime in the past a value for a population parameter such as a mean or a proportion. And so this is it's sort of accepted, and we call that the null hypothesis. The null hypothesis is just somebody's estimated value for an unknown population parameter, such as a mean or proportion. It's unknown, but somebody has, through some previous research or whatever experience, they've come up with their own hypothesis about that value. So there's a value, it's the null hypothesis, and then somebody comes along, like a researcher, and claims, hey, I don't think that's true, and I'm going to try to prove it using the sample that I've gathered. And that's called the alternative hypothesis. So it's competing. It's something competing with the standard null hypothesis. So the null hypothesis is an accepted hypothesis. When we write it symbolically, we'll always use an equal sign. And the symbol that we're going to use for the null hypothesis in general is an H for hypothesis with a little 0 next to it. And this is pronounced H naught. Naught means 0, or H sub 0. I've heard people say it both ways, but in both cases, it means the null hypothesis is H with the 0 next to it. An example of writing a null hypothesis, these are just examples, the numbers don't mean anything, all right? You would write H naught, and you would write a colon next to it. And then you'd use your Greek letter. Well, in this case, a Greek letter. The population letter for the mean is mu. You use mu. And you always use an equal sign for a null hypothesis. In this case, we're just saying mu is equal to 5. Or if it's a proportion, this is another example of the way a proportion would look like for a null hypothesis. Again, H naught colon P, which is the population, if this is a symbol for a population proportion, equal to 0.35. This is just an example of what it looks like, all right, when you write it. You're not going to write English, you're going to write symbols. All right, so that is the null hypothesis. Again, always an equal sign in the null hypothesis. The alternative hypothesis, the competing one that the researcher is offering, has one of 3 symbols. It's either going to have a greater than symbol, a less than symbol, or a not equal to symbol. We always use H sub A, H with a little a next to it, as a symbol for the an alternative hypothesis. So H sub 0 is for the null hypothesis. H sub A is for the alternative hypothesis. And you always, again, put a colon next to it. If the alternative hypothesis is for a mean, we're going to use mu. And there's 3 possibilities for the alternative hypothesis. Either the alternative hypothesis is saying that mu is, in this case, because mu is equal to 5 for the null, it's either going to be greater than 5, less than 5, or not equal to 5. One of these 3 is going to be the alternative hypothesis. All right. If it's a proportion, again, greater than, less than, or not equal to would be the 3 possibilities. Only one of these 3 will be selected. Now, how would you know in a word problem? Well, the wording of the problem will tell you. It should be clear that the alternative hypothesis is some value greater or some value less. If they don't say much about greater or less, then most likely they're saying not equal to, all right? Because something not equal to could mean less than or greater than. So when you write a hypothesis test, the first step is to write the null and alternative hypothesis symbolically, not in words, symbolically, just like this, right? And remember, the null hypothesis always has an equal sign, and the alternative does not have an equal sign. It either has greater than, less than, or not equal to. Now, in hypothesis tests, just like in a jury trial, if you have a jury trial and a criminal trial, and if you know anything about criminal trials, if you've watched enough shows about it, or if you've actually been on a jury, you know that the judge will instruct the jury that the person who is accused of some crime is assumed to be innocent at first. So that is the null hypothesis. We're assuming that person is innocent. In a criminal trial, the alternative hypothesis would be the person is not innocent, they committed the crime. All right, so that's a simple case, but it gives you the idea that the criminal is not considered to be have done the crime. The prosecution, the person who the state or whoever is providing the evidence against the potential criminal, they have to prove it. They have to provide enough evidence, which is beyond a reasonable doubt. That's the way they say it in criminal trials, to say that that person committed the crime. In a criminal trial, we don't typically you don't know if the person committed the crime or not, and that's why the evidence has to be considered. The same thing in a statistical test, right? The null hypothesis is assumed to be true. And then the sample that you've gathered, the question is, has it provided enough statistical evidence to say that the null hypothesis is not true, and the alternative hypothesis is probably true? So that's what the test is all about, all right? So we assume initially that the null hypothesis is true, and we want to see if there's enough statistical evidence otherwise. So what are we looking for? Well, if the null hypothesis is about a population mean, okay, and it gives it like a value of 5, for example, we look at the sample data and see how far away is the sample mean from the proposed population mean. Is it far away or is it close? Now, if we would just ask that question in general, some of you would look at the sample mean and say, yeah, it seems far away, and some of you would not. There might be some disagreement about whether the sample mean is far enough away from the population mean to say it's highly unlikely that if we got that sample mean, that the population mean is not is that value of 5. All right, so we have to see how far away do we need to be. How far away does the sample mean need to be from the population mean to say, I think that population mean is not quite right. It seems to be greater than. It seems to be greater than that number or less than that number. So that's really what we're trying to determine is how far away does the sample mean need to be to cast some doubt upon the null hypothesis. Now, again, if we don't have any numerical way of doing this, then people are going to disagree. So there has to be a numerical way, some procedural way of testing how far away is that, does that sample statistic need to be for you to reject the null hypothesis. So that's what we're going to learn how to do. Now, if we decide through the procedure that we've chosen, in this case, it's going to be randomization tests through StatKey, that there is enough evidence, then we state that the alternative hypothesis is this, the way we say it is that it's statistically significant. In other words, it's so far away from the null hypothesis that the alternative hypothesis is probably true. If there's not enough evidence, then we do not reject the null hypothesis. So that's how it works. All right. So either we're going to reject the null hypothesis or we're not going to reject it. Now, if we do not have enough evidence to reject it, it doesn't mean the null hypothesis is true. It could still be false. So we never say, if there's not enough evidence, we never say we accept the null hypothesis is true. We never say that because it still could be false. What we do say is that there's not enough evidence to say that it's probably false. All right, so that is the basics of hypothesis testing. Now, let me show you this chart here, which is pretty much in every statistics book in one form or another. And this sort of explains the idea of hypothesis tests. Along the top here is an unknown reality of the population. In other words, somebody has proposed a population mean, but it's still unknown. If it was known, we wouldn't have to do a test, right? We would just know what it is. But so the unknown reality, the reality that's out there is that either the null hypothesis is true or it's false. Okay, it's either true or false. We don't know, but we're going to use our sample statistics to test to see if there's enough evidence to think that it is true or whether it's false. So we run a test. Now, we're not going to run the test on the entire population. We're running it on a sample, all right, which is a lot smaller than the population. So we run the test. We run through our procedure, and then we're going to have one of two choices. We're either going to reject the null hypothesis or we're not. All right, those are the two choices. Let me run it through it again. We're going to reject the null hypothesis, which means we find the evidence to be significant against the null hypothesis, or we're not going to reject the null hypothesis. That means it's not significant, the evidence. The sample is not providing enough evidence. So what do these 4 boxes represent? The 4 boxes represent the intersection of reality with the test, the results of the test. For example, in this box here, upper left box, what it says basically is that we're rejecting the null hypothesis, when in reality, the null hypothesis is true. Now, remember, we don't know whether it's true or false, but let's assume that it's true. If we're rejecting it as if it was false, but in reality, it's true, that's an error. We made an error when we do that. And that's called a type 1 error. So type 1 error is when we reject the null hypothesis when the null hypothesis is actually true. Now, if we reject the null hypothesis and it's actually false, we've made a correct decision, right? Because when we reject the null hypothesis, we're accepting the alternative hypothesis. So by rejecting the null hypothesis when it's actually false, that's a correct decision. So the test was correct in that case. The other possibility for the test is that we do not reject the null hypothesis. Suppose we do not reject the null hypothesis when the null hypothesis is actually true. Well, that means we came up with the correct decision. If we do not reject the null hypothesis when it's actually true, that's a good decision, and that's fine. But what if we do not reject the null hypothesis when the null hypothesis is false? Well, that's an error. And that's what we call a type 2 error, is when we do not reject the null hypothesis when it's false. Now, going back to that example with COVID, if the null hypothesis is that you do not have COVID, okay, and the alternative hypothesis is that you do have COVID, okay, and if you reject the null hypothesis, which means the test shows that you have COVID, but you actually don't have COVID. Remember, the null hypothesis means you don't have COVID. That's an error, right? That means that the test says you have COVID, but you don't have COVID. That's what's called a false positive, right? The test shows positive means you have COVID, but you really don't. The other type of error down here would be the case where we do not reject H0. That means the test that does not show COVID when you actually have COVID. That's called a false negative. So false positive would be similar to the type 1 error, and a false negative would be similar to a type 2 error. All right, you may want to write that down. It's mentioned in your book. All right, so we have 2 errors, type 1 and type 2 error. We have 2 results that are correct. Now, what is a researcher? What's a researcher trying to do? They're claiming that the null hypothesis is false. They have an alternative hypothesis. So their goal is to reject the null hypothesis, right? That's what they want to do. And they're hoping that this box is the correct result. They're rejecting the null hypothesis, and the null hypothesis is false, which means their hypothesis, the alternative hypothesis, is true. That's what they're trying. That's their goal. So what is the error that they're trying to minimize? That's this type 1 error, right? Because they're trying to reject the null hypothesis, but there is a chance that the null hypothesis is actually true. So they want to make sure that that error is small. This type 1 error is small. Now, the probability of a type 1 error is called alpha. All right, alpha is just a Greek letter. And in this case, it's used for the probability of a type 1 error. Now, the probability of a type 1 error is the probability that you reject the null hypothesis when the null hypothesis is true. The letter beta, the Greek letter beta, this letter here, is the probability of a type 2 error. It's a probability that you do not reject the null hypothesis when it's actually false. Now, beta is something that is used in a more advanced type of course, where they go through it a little bit more than in this type of course. So we're not going to spend much time with beta. Just know what the definition of it is. That's all you need to know. But we will be using alpha. Now, the other thing that's mentioned in the book is called the power of the test. I mentioned it to you as we were flipping through it. And the power of the test is the probability that we reject the null hypothesis when it's actually false. In other words, this box right here, the probability of this result, which is the result that the researcher wants, is called the power of the test. Again, it's the probability of rejecting the null hypothesis when it is actually false. Now, the only thing you need to know, again, like beta, is that you just need to know the definition. This, again, is used in a more advanced, typically a graduate level course in statistics, definitely not on this level. So the only thing you need to know is this definition. So knowing, when you take your tests, take your final exam, it'd be good to have this particular sheet with you so you can refer to it. All right. Now, another name for alpha, which is the probability of a type 1 error, is called the level of significance. Now, why is it called the level of significance? The reason is because researchers, before they actually do any research, before they even take their sample, they want to determine the highest amount of type 1 error they're willing to tolerate. Remember, they're trying to reject the null hypothesis, but they don't want a situation where they're rejecting the null hypothesis when the null hypothesis is actually true. So they want to make sure that this alpha is a small number. Remember, it's a probability. So probability is between 0 and 1. Typically, alpha is something around 0.05 or 5%. Some researchers might use 1% or 0.01, or they might use 10%, 0.10. Whatever they may use, that is called the level of significance. Now, it says here that the researcher will determine this before they begin the research. And they're going to, and once they do their research, they're going to use this alpha to determine if the sample statistic, either the sample mean or sample proportion, is sufficiently far away from the hypothesized value of the null hypothesis to make it unlikely that this null hypothesis is true. In other words, is it possible that the null hypothesis, through just normal variation, created this sample statistic, sample mean, or is it highly unlikely? If it's highly unlikely, we're going to reject the null hypothesis, and we'll say that there's enough evidence to claim that the alternative hypothesis is probably true. Okay? Now, if through the procedure that you'll be learning, we say that the sample statistic is not sufficiently far away from the population value mentioned in the null hypothesis, then the decision is not to reject the null hypothesis. Okay. Now, in hypothesis testing, we have, again, our two hypotheses, the null hypothesis and the alternative hypothesis. The number that is in the null hypothesis has to be matched in the alternative hypothesis. That's always true. The null hypothesis decides having a population parameter, mean or proportion here, and the equal sign here has to have some number here. And the alternative hypothesis has that same number. All right, so the numbers match. But what's different in the alternative hypothesis is this, whether it's greater than, less than, or not equal to. It's this middle part here. Now, you will determine, as you'll see in the examples on Wednesday, which of the three possible types of hypothesis tests that you have. Whether, in this case, if there's a not equal sign in the alternative hypothesis, this is called a two-tailed test, which means that your sample mean could be much less than the population mean for us to reject the null hypothesis, or it could be much greater than mu. All right, could be either one. And the researcher doesn't care whether it's less than or greater than in terms of rejecting the null hypothesis. Again, that'll be made clear in the writing of the problem. Now, if we have one of these two-tailed tests, And suppose the researcher selected, before they did the research, that their level of significance is 0.05 or 5%. One way of doing the hypothesis test, and there's a second way, which I will explain to you on Wednesday, and it is mentioned in the video that I'll be showing to you today. Basically, this one method here is called the rejection region method. All right. Now, what we do is for the two-tailed test, only for the two-tailed test, we take our alpha and divide it by 2. And we put half of it on the right tail of a bell-shaped curve, and we put half of it on the left tail of a bell-shaped curve. We take our mean, which is proposed in our null hypothesis, and we place it in the middle. That's our mean. And this is what we do. We say, all right, the area under the curve here is 2.5% of the total area. All right, the small area here, that's because half of alpha is 0.025, so it's 2.5%. And then we have another 2.5% on the left. We call both of the regions, which are part of that area, rejection regions. And the way it works with the rejection region method is that we take a look at our sample mean in this case, and see if it's within one of these rejection regions. In other words, we go along the x-axis here, and we plot where the sample mean is. And if the sample mean is inside one of these areas that are shaded in, these 2.5% areas, then we automatically reject the null hypothesis. All right? And we say it's not, we reject it and we go with the alternative hypothesis. If, however, the sample mean is inside this area that's not shaded, somewhere along this number line that's not shaded, in this 95% non-rejection region, we say that there is not enough evidence to reject the null hypothesis. In other words, the sample mean is not sufficiently away from 10 to say that we have enough evidence to reject 10 as the population mean. If it's in one of these shaded areas, we say it is sufficiently away, and it's highly unlikely that the population mean is 10. That's called a two-tailed test. This is one way of doing it. Again, there's a second way, again, which will be explained in the video today and also on Wednesday. But I think as an introduction, this is an easier way of understanding hypothesis tests as opposed to the other method, which I'll show you again later. If the alternative hypothesis has less than in it, we use what's called a left tail or lower tail test. All right? People use both those terms, left tail or lower tail. It means the same thing. Again, we put our, now in this case, it's a proportion. We use P as a population proportion. We say that the null hypothesis says that the population proportion is equal to 0.45. We do our bell-shaped curve. We put 0.45 in the middle. And the alternative hypothesis is that P is less than that. All right, so something in the researcher's claim says he or she thinks that the population proportion is significantly less than 0.45. So what we do in this particular method is we take our entire alpha, the level of significance. So in this case, the researcher picked 1% or 0.01. And what you do is you put it all, the whole area, the whole 0.01 or 1%, you put it all on the left tail, under the left tail. And that becomes your rejection region. And then you have the rest of it, the 99%, as your non-rejection region. Once again, you plot your sample proportion somewhere along here. If it happens to be in this region here, then you reject the null hypothesis. If it's in the non-rejection region, you do not reject the null hypothesis. And then finally, we have another type of test called the right tail or upper tail test, where the alternative hypothesis has a greater than symbol. So the researcher believes that the true population mean is greater than 100 in this case, significantly greater than 100. So in this case, alpha, this researcher picked alpha as 10%, the probability of a type 1 error. The level of significance is 10%. They plotted the right tail is 10% like this. And they basically, and then they plotted 100 as the mean. And then they would plot the sample mean. If the sample mean is in the shaded area here, you reject the null hypothesis. If it's in the 90% non-rejection region, you do not reject the null hypothesis. But this is in essence what a hypothesis test does, okay? And it's based on this alpha, all right? But we'll get into that more later. Any questions about that? Now, don't worry if you're only understanding about 10, 20% of this, that's fine. It's not unusual. Repetition is going to be the way for you to know how to do this. So this is just an introduction to it. Now, what I'd like to do now is I'm going to go to the stat key. Let me make sure stat key is highlighted. There we go. But remember to get the stat key, you just type into your browser stat key, and then you'll see stat key lock, and then you come to this website here. Now, to get to the videos, so we're going to be working in this third column on Wednesday. Don't worry about it for now. I'm going to show you where to find these videos again. So we just click here, and then videos along the left-hand side. And the one we're going to go over today is called Overview of Randomization Tests. It takes about 20 minutes. We have a little more than a couple minutes, more than 20 minutes left. So we'll start playing this, and should be able to hear it. If you don't hear it, please just yell out that I just clicked the audio. You should be able to hear it.
Hi, I'm Carrie Locke Morgan, and I'm going to go through a brief introduction to randomization tests. So the motivation for a randomization test stems from the definition of a p-value, the probability of getting a statistic as extreme as the observed statistic if the null hypothesis is true. So let's break this down into two parts. So we first want to know what kinds of statistics would we get if the null hypothesis were true? And then secondly, once we have step one completed, how extreme is the observed statistic? So this is really the foundation for a randomization test. More formally, a randomization test consists of two steps. The first step is to simulate new statistics, assuming the null hypothesis is true. And then once you have these statistics, find the proportion of these simulated statistics that are as extreme as your observed statistic. I'm going to illustrate this process with three different examples. So the first example is Paul the Octopus, and I gave you a YouTube link if you want to watch it later. But to summarize, Paul the Octopus predicted 8 World Cup games and predicted them all correctly. So a big question in everyone's mind, is this evidence that Paul actually has psychic powers? So maybe we can't quite get at that question, but we can answer the question of how unusual would this be if he was just randomly guessing, with just a 50% chance of guessing correctly. So to put this into a more formal hypothesis testing framework, we're doing inference for a single proportion, where this proportion P is the proportion of correct guesses of all times that Paul would predict a World Cup game. Our null hypothesis is P equals 0.5 versus our alternative that P is greater than 0.5. In a randomization test, the first step is to simulate new statistics, assuming the null is true. In this case, we want to know what kinds of statistics we would observe if P equals 0.5. Well, luckily, we can simulate this just by flipping coins. In other words, we can simulate a new statistic by flipping a coin 8 times, because the sample size is 8, and recording the proportion of heads, or equivalently the proportion of correct guesses. And if we repeat this process many times, we come up with a distribution of new statistics, assuming the null hypothesis is true. Of course, if we want to repeat this many times, we're not going to sit there flipping coins over and over again. We're going to turn to technology. So there's lots of different options for technology for conducting a randomization test, and we give manuals from many of the common software packages. But for ease of illustration, here we're going to use StatKey, which is free online software that we've developed to accompany our textbook. So this is the homepage for StatKey. Here we're going to be focusing entirely on this randomization hypothesis test column. Here we're doing a test for a single proportion. And our count is 8 because he got 8 correct out of a sample size of 8. So this brings in our data. We see our sample proportion of 1. Now we're going to generate one randomization sample by clicking on Generate One Sample, which is essentially just flipping a coin 8 times and counting the number of heads. So in this particular simulation, we happen to get 5 out of 8 heads, or 5 out of 8 correct guesses, for a sample proportion of 0.625, which is then plotted down here on the randomization distribution with a dot above 0.625. We can do this again, just flipping 8 coins, or flipping a coin 8 times. Here we got a sample proportion of 0.5 for 4 out of 8 correct guesses. So we see a dot appear above 0.5. We can do it again, 0.5 again, this time 0.75. You can do this repeatedly. You can start to see a distribution building up. Each time we're simulating a new statistic, assuming the null hypothesis is true. And once you get bored of generating samples one at a time, and once students start to understand what's going on, you can jump ahead and generate 1,000 samples. So now we have a distribution of statistics that we would observe if the null hypothesis were true. So now that we have this distribution, the second step in a randomization test is to find the proportion of these simulated statistics that are as extreme as your observed statistic. Or in other words, in this particular case, we want to know what proportion of these simulated statistics are as extreme as the observed proportion of p hat equals 8 over 8, or 1. So let's go back to our distribution of statistics, assuming the null is true. And we're doing an upper tail test, so we want to look at the right tail, and we want to see how extreme our observed statistic of 1 is. So we find 1 on the x-axis, and above it, in this little blue rectangle, we see that, in this case, 4 out of the 1,000 simulated statistics are as extreme as our sample proportion of 1. So what have we just done here? We've developed a distribution of the statistic, in this case a sample proportion, assuming the null is true. We then want to find on the x-axis our observed statistic, and then measure its extremity by calculating the proportion of statistics as extreme as the observed statistic. And this number is our p-value. So in this particular experiment, the probability of Paul guessing all 8 out of 8 correctly, if he really is just randomly guessing with p equals 0.5, is 0.004. And just in case you were wondering, this is very close to the theoretical value of 0.0039 that you can calculate exactly. The more randomizations you do, the more precisely you can get to this number. All right, so that's Paul the octopus, and that's our single proportion example. Now we're going to jump into an example with difference in proportions. So we're going to look at an example on cocaine addiction. So in a randomized experiment on treating cocaine addiction, 48 people were randomly assigned to take either disipramine, a new drug, or lithium, an existing drug. And our response variable is whether or not a patient relapsed. So the question of interest is disipramine significantly better than lithium at treating cocaine addiction? You may notice this is a simple difference in proportions hypothesis testing scenario. All right, so this is a randomized experiment, so just to take you through this. So we have our 48 people to be treated with either disipramine or lithium, and we randomly assign the units to the treatment groups. And this is the random process. I won't take you through all of it, but eventually they all get assigned. We conduct the experiment or give them the drug, wait and see what happens, and then observe the relapse counts in each group. So you'll notice that under the new drug, disipramine, 10 relapsed while 14 didn't relapse, and under the old drug, 18 relapsed while 6 didn't relapse. So the difference in proportions is negative 1/3. The crucial question is this difference more extreme than we would expect to see just by random chance? So is it plausible that just randomly more relapsers happen to be assigned to the old drug group, or is there actually something going on with the drugs? All right, so going back to our first step of a randomization test, we want to simulate new statistics, assuming the null hypothesis is true. So in this case, we want to know what kinds of statistics would be observed just by random assignment to treatment groups if the drugs are the same regarding relapses. So if neither drug causes more or less relapses. So we can do this by simulating new randomizations and just keeping relapse status unchanged. Because basically we're assuming that it doesn't matter which group you get assigned to, you're still going to relapse or not relapse, as you did in the original experiment, because we're assuming the null hypothesis is true. We want to see what would happen just by the random allocation to treatment groups. So we have our data, we pool everyone back together, and we re-randomize or simulate another randomization. This, by the way, is why it's called a randomization test, because we're simulating randomizations most often. And as we're doing this, we're keeping the relapse status fixed because we're assuming the null hypothesis is true. So in this particular randomization, the new drug had 16 relapses, while the old drug had 12 relapses, for a difference in proportions of 0.167. We can do this again if you want, and we get a difference in proportions of 0.25. So ideally, we'd like to repeat this process many, many, many times to really get an idea for whether our observed difference in sample proportions is actually extreme. So we're again going to turn to StatKey, and now we're doing a test for difference in proportions. So in original data, we had 10 out of 24 relapsing under the new drug and 18 out of 24 relapsing under the old drug. And we see our difference in proportions of negative 1/3. So if I click generate one sample now, I'm going to reassign the units to treatment groups, keeping the relapse status the same as we just did in the PowerPoint slides. So I'm simulating statistics that I would get just by random chance or just by the random division into treatment groups if there really is no differences between the drugs or if the null hypothesis really is true. So in this particular randomization sample, we got a difference in proportions of negative 0.25, which is plotted with a dot here on the randomization distribution. And we can do this again and again, building up randomization statistics or simulating new statistics, assuming the null is true. And we can go ahead and generate 1,000 samples, or even if we want to, maybe a couple more, and get up to 4,000 or 5,000 samples. The more samples you generate, the more accurate your p-value will actually be. So now we have a distribution of statistics, assuming the null hypothesis is true. And the next step is to see how extreme our observed statistic of negative 1/3 actually is. So in this case, we're doing a lower tail test. We want to look at the left tail because we want to see if the proportion of relapses under disipramine is less than the proportion of relapses under lithium. So we're looking at finding negative 0.333, our observed statistic, on the x-axis, and calculating the probability in the tail. So in this case, we see the proportion of simulated statistics as extreme as our observed statistic, or in other words, the p-value is 0.019. So it looks like there is significant evidence that disipramine is better than lithium. So just to take you through this again, we have our distribution of the statistic, assuming the null is true. We find our observed statistic on the x-axis and calculate the proportion as extreme as the observed statistic. Or in other words, we find that the probability of getting results as extreme or more extreme than those observed, if the null hypothesis is true, is about 0.02, which in this case is the p-value. All right, so that's our second example. We've done a proportion, we've done a difference in proportions. Now we're going to turn to a difference in means. So we're going to look at sleep or caffeine for memory. So this is based on an experiment in which students were given words to memorize and then randomly assigned to either take a 90-minute nap or to stay awake and take a caffeine pill. 2.5 hours later, all students were tested on their recall ability. And the question we want to answer is either sleep or caffeine better for memory? So in this case, our parameters of interest are the mean number of words recalled if a student either sleeps or consumes caffeine. Our null is that the two means are equal or that there is no difference in means. And our alternative is that the two means are not equal or that there is a difference in means. All right, so here's our data. The sleep mean turns out to be 15.25. The caffeine mean turns out to be 12.25 for a difference in means of 3. Big question, is sleep actually better than caffeine for memory, or did the people with better memory just happen to get randomly assigned to sleep? So to answer this, we need to actually do a randomization test. We need to simulate what would happen just by random chance. So again, here's our data. What we want to know is what kind of results would you see just by random chance if there were no difference between sleep and caffeine? So just like we did with the cocaine addiction problem, we're going to basically reassign all the response values to different treatment groups. Or we're going to see what would happen just by the random assignment to either sleep or caffeine if whether they sleep or have caffeine has no effect on the number of words recalled. So we're going to keep the response values unchanged and randomly reassign people to either sleep or caffeine. This is, again, to simulate statistics that we would get if the null hypothesis were true, or if there is no difference between sleep and caffeine for memory. In this particular randomization, our sleep mean is 14.25, our caffeine mean is 13.25, so we have a difference in means of 1. Ideally, we'd like to do this many times, so again, we're going to turn to technology. So we're going to go to a test for difference in means. I'm going to bring up the sleep caffeine words data. So here you can see the data, the original data that we were looking at with a difference in sample means of 3. So if I click now generate one sample, I'm randomly reallocating each value to either the sleep or the caffeine group to see what would happen just by random chance or just by the random assignment to treatment groups if there is no difference between sleep and caffeine for memory. So in this particular randomization sample, we got a statistic or a difference in means of negative 1.67, which is plotted down here on the randomization distribution. We could do this a couple more times, speed it up, and we can generate 1,000 samples. So now we have a distribution of the statistic, or in this case, the difference in means, assuming the null is true. Again, we want to see how extreme our observed statistic is. So in this case, we have a two-sided alternative. So we're going to look at both tails, and we want to see how extreme our difference in means is of 3. It actually already came up right here. So we're looking at our observed statistic of 3, and we see that on either side, about 0.025 of the values are as extreme as 3. We have a distribution of the statistic, assuming the null is true. We find our observed statistic on the x-axis, and we look at the proportion as extreme as that. It's going to vary, values are going to vary a little bit from simulation to simulation. Here we have 0.024, whereas in the simulation I showed you, we have 0.025. But that's okay. If you're worried about that, you can just generate more randomization samples to get a more precise estimate. In this case, we're looking at both tails. So the p-value is the proportion as extreme as the observed statistic, which is the proportion in both tails, or in this case, 0.048. All right, so you now know how to conduct a randomization test. First step, simulate new statistics, assuming the null hypothesis is true. Second step, find the proportion of these simulated statistics that are as extreme as your observed statistic. And the nice thing about a randomization test, besides the fact that it helps students intuitively understand the definition of a p-value, is that it's always the same process, no matter what you're testing. So there's not a whole long list of different formulas to learn. It's really just these 2 steps. All right, thanks for listening. And additional information can be found at our website, www.lock5stat.com.
Okay, so that's the video that explains a little bit about randomization tests. And that's what we're going to be using on Wednesday. We'll do some live examples with this. And I'll show you how to do one-tail tests, the left and right tail tests, the two-tail tests, and with the different types of randomization tests that we'll be using. So there'll be quite a few examples. All right. Any questions so far? Nothing? Okay. Probably enough. All right, so that's all we'll do today. All right, we'll stop now and stop the recording.